already told him that.
Okay. Here's something to hide. I think we should start this session. I have to remind all speakers that they should absolutely keep in time, because there will be a photographer coming after this session, and this guy has only just 5 minutes. So this is what you no, you said minus 5 minutes. Yeah, yeah. Okay, so that everybody knows. So I will strictly get up and take off the micro if you don't stop in time. I'm sorry for that. I don't want to be rude, but in this case, I was told I have to be like that. So we come to the first talk, which is given by Eric Cocaine. It's on local structure and spin configurations in manganese-doped strontium titanate. Please.
Thank you. Is this microphone live?
That's enough.
Thanks. I'd like to thank my coworkers on this project at NIST, and also to the organizers for giving me the chance to talk here. Looks like a nice session on strontium titanate and illuminates. So I'll begin by discussing the motivation for this study, and it's multifold. First of all, it's the possibility of the multiferroism in strontium titanate doped with manganese. So strontium titanate's well known, has a anti-ferrodistortive ground state, but it also has a near ferroelectric instability, and so in thin film strontium titanate, it's possible to observe sometimes the ferroelectricity. So if you dope with a magnetic ion such as manganese, there's opens the possibility of multiferroicity. In any case, there's certainly going to be local polar and spin moments when you dope that. And that also makes a good introduction to the last talk in the session by Dabrowski. I think he's going to be talking about multiferroic with things with manganese doped. And another topic is ion conductivity. So typically in perovskites, the main kind of ion conductivity would be oxygen ions moving, and that would be essentially due to having an oxygen vacancy, which is mobile. But oxygen vacancies are typically not the only defect. You can also have, for example, substitution for cations, and these might pin the oxygen vacancies and have a significant effect on the diffusion, as we shall see. And finally, there's just its basic science that multiple defects are possible in this system. And so in order to establish experimental observation of them, you have to know the local structures and what you're looking for. So basically, this is a pretty common DFT format. I should point out that it's using PBE sol instead of PBE because it tends to give the lattice parameters better than that form of GGA. And also we're using Hubbard U, and in the case of manganese J corrections for the transition metal ions. Surprisingly, these values that we're using have been, in our work, we found them to be quite transferable between 3+ and 4+ charge states for both of them. So as I've discussed before, at room temperature, the average structure of strontium titanate is cubic. We find two different types of instabilities. One is the plus tilting, where the oxygen tilt is well known, but in phase in different layers, and the even more unstable negative tilting. And I should mention that in our linear response calculations, we did not find any ferroelectric instability in strontium titanate. That contradicts to the abstract in the next talk where they say they do. I'll have to go back and recheck it. It's something simple, probably like a different lattice parameter used. And so we can calculate the ground state, allowing all the ions and the lattice to relax. We obtain what looks like the experimental pattern that occurs below about 105 Kelvin. Whereas if we fix the lattice parameters to the value for cubic lattice parameters for strontium titanate at room temperature, a rather different tilting pattern is possible. And so these are the kinds of things that will spontaneously happen if you add defects, so you have to be careful to account for them or not account for them. Moving on, we've kind of calculated what I'll call a diffusion phase diagram. It's not a phase diagram. It's the single most stable defect at least between oxygen vacancies, manganese substitutions, or combinations that occurs as a function of the oxygen and the strontium chemical potential. And in here, this polygon is the region where strontium titanate is stable. So these kinds of substitutional defects and a defects complex with an oxygen vacancy and a manganese substitution for titanium are expected to be the most important. So I'll begin with the oxygen vacancy study, going the defects from the most simple to the most complicated. Here's the distances between the ions without the oxygen vacancy, and here's with the oxygen vacancy on the bottom. And to the right, I show you the band structures. I must apologize. I did these calculations quickly and with a rather small set of K points, and so really there should be not a gap here. And here is, for reference, a more appropriately done calculation with tetrahedral interpolation. In either case, there's a measured, DFT band gap is 2 eV. It underestimates the experimental band gap, which is about 3.2. Indirect gap is well known. What I'm really showing is that adding an oxygen vacancy in this picture, you simply shift the bands and you occupy some titanium, essentially unoccupied titanium levels get occupied by the electrons donated by the oxygen vacancy. And so this is simply a one electron cone sham picture. There's no polarons being looked at or anything exotic. We tried all we could to make charge localized on titanium next to the oxygen vacancy so that you would have 3+ titanium, and that didn't work. It just disperses over different sites. And also we tried to make magnetic moments, and those were not possible. Next defect is fairly simple. It's manganese substitution on titanium. And as we'll see in a later talk, it tends to be it's a 4+ ion. It substitutes well. It's a little smaller. Here, there is a distinction between the up and down electrons when you include the magnetism. It's polarized into, while there's 3 occupied D plus electrons that all have the same spin, but they're deep inside the valence band, so you don't even see them on the diagram. It's more interesting when you do manganese substitution for strontium. So if you look at the Shannon ionic radii, it shouldn't even happen because the radius of manganese is so much smaller than strontium. Nonetheless, if you grow it under strontium poor conditions, you do get manganese substitution on the strontium site. And so you have to look at the possibility that it off-centers to lower the energy. And it certainly does. So if you just naively start with cubic symmetry and relax it in different directions, you'll find an order of lowering energy. The 110 displacement would be lowest. Interestingly enough, the bond of the direction it's moving is longer than the 4 around it if you carefully relax. However, this is not the full picture. If you allow for the oxygen tilting, you can get further lowerings of energy. So in fact, if we allow everything to relax and we carefully try all possibilities of the near neighbor ions moving, we find that this kind of tetrahedral looking coordination where the manganese on center is the lowest, at least for this concentration of 6.25% that we studied. But if we fix the structure at the cubic lattice parameters, so this is kind of what you might consider happening at a lower defect concentration, then the geometry is different. It does move off center by about 0.3 angstroms, but it's in there's trichemic symmetry. It doesn't move in any special direction, and it's hard for us to rationalize why that should happen, but that's what we find. Those results are for 0 temperature. They're DFT things, but interesting things happen at finite temperature. So dielectric relaxation studies show some resonance, and depending on the fit you do, you can do things to Arrhenius law fits, so they show a barrier, which is concentration and temperature, concentration dependent, I should say. And if you take these results and extrapolate them to our concentration that we've studied, you would get a barrier of like 90 millielectron volts and a characteristic attempt time of 10 femtoseconds. And so we can actually play with these numbers and see if we can use ab initio molecular dynamics to reproduce them. I should point out that we're way down in this part of the phase diagram and the timescales that we can actually achieve with a fully atomistic molecular dynamics. But we plug ahead. First, we looked at the room temperature, and according to the Arrhenius law, there should be maybe 1,000 femtoseconds between events. I plotted here a typical manganese substitution on strontium site and the distances to its 12 neighboring oxygens over time. And what happens in this thing is that here's two different initial configurations, and things move around a bit, but at the end, the neighbors are the same as at the beginning. So it's not clear that anything is jumping around other than the little fluctuations. So then we simulated at 750 degrees. At that point, the predicted jump time is only 100 femtoseconds, so many events should occur in the 1 picosecond simulation that we did. And indeed, you see a lot of changes. So I've highlighted in bold the one particular oxygen in each case, and you can see that over time it goes from being the closest one to the farthest one away to being the closest one, and down here also farthest away, closest, farther away. You can't really just look at it and get a flip time, but it seems to be things happening around 200 femtoseconds compared with the predicted 100 femtoseconds, or the experimental 100 femtoseconds. Given that those were extracted from log-log fits, the discrepancy is not very big. So it's nice to see. Here is the video I was going to show you. I practiced it ahead of time and found that the media player is not available on this laptop, so at least I know that I can't show you. But what would briefly happen is that you actually get a lot of oxygen movement. So the oxygen is moving around the manganese a lot more frequently than the manganese jumps from site to site. So things are quite complicated. In a paper that my colleagues did at the beginning of the decade, they looked at the manganese local environments for substitution on the two sites using XAFs. For at least the strontium substitution, all they considered was a displacement in the 001 direction. They found that 4 short neighbors works very well. Well, because of this work, we're reinterpreting and reinvestigating it. So it does appear that the 4 neighbors, 4 short oxygen distances is good, but it's not because it's displaced along 001. So now I'll move to the defect complex where the manganese substitutes back on the titanium site, but there's also an oxygen vacancy. So here I show the manganese, and I've labeled 1, 2, 3, 4 different positions with respect to it. In our periodic unit cell, the 4th neighbor was the farthest possibility that we can investigate. And so having calculated the energy of several of them, we find that the binding energy is of order 1 eV for the closest neighbor distance, and this agrees with the previous computational work. Barium titanate, so it's a different system, but it's NASA, Nomov, and Cohen looked at it and found a similar thing, and also some kind of empirical potential study shows that it binds with about 1 eV. So that's substantial. If you have manganese substitution, the oxygen vacancies will tend to pin there. The electronic structure, now it's more interesting. The electrons that are donated by the oxygen vacancy go when they fill additional manganese up states, and there's so it's 5-0 high spin state. There's no occupation of the down spins, and the geometry is I guess that moves a little away from the defect, and the oxygens in the equator move away a little from the manganese. So this agrees with the Cohen and co-worker study in the case of barium titanate. Things are more interesting when we looked at the farthest separation between the oxygen vacancy and manganese substitution, because through trial, error, and different initial conditions, we were able to actually get 4 different stable spin states. So counting the up and down electrons, you can see them here. The 4-0 case is an example of Jahn-Teller distortion. So that's why I show the splitting of the levels and how it lowers the energy by having this electron lower than the 3 under 2 splitting for pure octahedral coordination. And so, yeah, and it also gives a characteristic Jahn-Teller distortion. So in this case, it happens to have a short axis, but the other ones, in any case, depending on the spin state, you definitely have noticeable changes in the distances between manganese and oxygen. And also, if you see how many spins go into here, you can have manganese 2+ or manganese 3+. In the case where you have the 3+ state of manganese, the extra electron goes into the titanium-oxygen conduction band, kind of. So we tried really hard to see if we can get the manganese to stabilize in the 4+ state like it does for a simple substitution, but we were not successful. But we had looked at this GGA plus U, we looked at it and saw what would happen if you varied the value of U. And in this case, it actually changes the predicted ground state. So this is quite interesting, because do you really trust for predictive abilities that if you found that you could fit U equals 2.8 for manganese based on the Bixbyite manganese 203, that it should also apply to a manganese substitution in strontium titanate? So, if it's not really transferable, then you can easily have a different effective value in that system, and you might have a different spin state for this defect complex. Therefore, it's a case where experiment will have to be used in tandem with theory to establish what kind of spin moment happens in this defect. And here's pictures of the electronic states in each case. You can see a variety of gap states and difference between having some occupied, let's see. Yeah, so here in these cases, we have some occupied down states, and here you don't, etc. So I'll jump to conclusions to keep us on time. Basically, we looked at the manganese substitution in strontium titanate for both the A and the B sites and the defect complex with an oxygen vacancy and a manganese substitution. And as in everything, things are more complicated than you would think at first. So I would thank you for your attention.
Thank you very much, and thank you for staying in time. So we have a couple of minutes for, please.
Yeah.
If we apply, how about you, especially at the titanium site, it usually destroys the ferroelectricity.
I hadn't realized. So this other comparison with the
oxygen, even oxygen has much effect. So there's no contradiction.
All right, contradiction solved.
It's a pity, isn't it? Any other comments or questions?
I had a quick question on the phase diagram, the defect phase diagram you showed
Sure.
at the beginning. So presumably the energies of those different defects would also depend on the Fermi level?
Yeah, they would also depend on the Fermi level. This was a quick study where everything was
The next speaker
everything was kept neutral, but there are papers where they show the effect of the Fermi level, and that will, just changing the Fermi level will change which defect is the lowest in energy, in addition to changing the chemical potentials.
Any more comments or questions? Then we come to the second talk of this session, which is apparently not, which is, as we just heard, not in contradiction to the first one. And it will be given by Professor Watanabe, and he's talking